Hello, dear students. Welcome to a new semester. In this course, our new course, Building Science 2, we are going to examine the properties of roofs and walls, which we can define as the building envelope. So in this video, let's start with the building envelope and the functions of its different parts. Let's take a look at the classification of the roofs based on forms. Here we have two main categories. We can create forms with lines and planar surfaces and curved surfaces. And we can finish the video with an drawing exercise for hip roofs. The first question that we can ask ourselves is, what are the main parts of the building envelope and what are their functions? From our previous semester, let's remember the definition of the building. Uh, the building is a new man-made environment created by people, created by man, and it's been created by selecting, enclosing, and reorganizing a part of natural environment. Here we have the natural environment, so we select and enclose and reorganize this part of the natural environment so that we can provide a suitable living area for the user, for ourselves. So we can define this part as the borders of the built environment, uh, and obviously that's the envelope of the building. In Turkish, we call this bina kabuğu, yapı kabuğu. And there's this outdoor environment, dış çevre, and indoor environment, iç çevre. And these two environments are constantly interacting, they are affecting each other. We can diagrammatize this in a simpler way. If this is the borders of the built environment, the building envelope, then there is this outer environment which encloses this envelope. And there's this indoor environment, and it's being included by the envelope. In the indoor environment, we have user, but we can have different types of users with different properties, biological properties, age, body sizes, different sociological properties, different psychological properties. But not only the humans can be the users, we can design built environments for the animals. And there are some physical properties that constitute the indoor environment, like light, uh, like sounds or noise, like air, like temperatures, either air temperatures or the temperatures of the surfaces. And there can be other people, a social environment in the outdoor area, other living creatures, plants and animals, and non-living entities, just like the sun rays, wind, air, and other man-made either environments, buildings, or vehicles. We can multiply the examples, of course, and they are constantly interacting, such as in the indoor area, the user needs a certain level of air temperature. If it's too cold or if it's too hot, that can be dangerous, even deadly for the user. So we need to maintain a certain level of temperature. But this indoor temperature is constantly affected by the outdoor temperature based on the climate of the area, the wind, and the sun rays, and many other factors. We can give another example out of sound. Based on the activities and biological properties of the user, they may require a quieter space, and if there are other vehicles, traffic, other people in the outdoor environment, all this noise can affect indoor environment in a negative way. But this interaction isn't always from outdoors to indoors and isn't always in a negative way. There can be a positive interaction between outdoors and indoors, or a negative interaction that originates from the indoor area and affects the outdoors in a negative way. Let's have another look. Let's imagine there are two different users, and one of them is sick, and this person is coughing, and it means that they are uh, distributing lots of viruses or bacteria in air, and these small living creatures can be airborne. They can stay in the air for a certain period of time, and if the other person breathes in through respiration, they can get sick too. So we need an efficient air cleaning system. Of course, we can have mechanical systems, but natural ventilation is much better in terms of economical uh, conditions, and it's healthier and it's more environmental friendly. So if we design a nice envelope, then we can create a positive interaction between outdoor area and indoor area. If there is a nice air movement in the outdoor area, we can have openings in the building envelope which will let this air movement inside, so that all the unwanted air pollutants can be swept away. So we can say that a building's performance, its ability to meet all the user requirements. If the user needs a quiet space, then providing that quiet space. If the user needs a warm air temperature, providing that space property for the user is directly related how these environments affect each other, and this interaction, this affecting is uh, it depends on, it occurs as the result of all the decisions made during the design, how we create the envelope. What kind of a space will be created inside this envelope? And what kind of interactions will this envelope create? That's the main question. And this semester's topics are, two main topics are roofs and walls, and learning necessary knowledge and examining good or bad examples in order to make correct design decisions. The main purpose of the boundary and the spaces is to provide a healthy and comfortable living environment for the user by protecting them from all negative effects. So that's what we need to focus on. We need to avoid or prevent all the negative features that can harm the user and indoor spaces. And we can let all the good things that the require will that the user will need in the indoor environment. We need to always aim for a positive interaction, either from outdoor environment towards the indoor area or vice versa. So this part, either it can be inclined, sloped like that, or it can be horizontal. That upper part is mostly defined as the roof, uh, the upper part of the envelope. And these vertical, also these can be inclined as well in different shapes. But generally, in general terms, these vertical parts are defined as the walls. First, we are going to cover the roofs, and probably after the midterm exam, we will start examining the walls. So let's start with the roofs. Roof is a building element. As you remember, we are covering elements in building science. In our previous course, Building Science 1, we did the building structure, the floors, foundations, and vertical circulation elements, stairs, ramps, and elevators. Roof is our new building element, and it's the highest part of the building envelope. But please do not just imagine this ordinary image right away. When we say roof, many people just get this mental image with this uh, orange-shaped tile roof with these inclined surfaces, sloped surfaces. That's only one of the examples that we can do. However, maybe you didn't notice there is this other building next to this old one, let's say, more traditional looking one. Obviously, this is a modern building. Maybe some of you know this building. It's the Jewish Museum designed by Daniel Libeskind. So I advise you to search for it, both for the architect and this design. And here we see a very extraordinary geometrical form, both for the building mass and the upper part. This is the roof, not only this orange-shaped sloping surfaces, but this upper part of the envelope. This is the roof of this building. So this is a museum. This is the old part, the first uh, part of the museum, but in time it's not efficient and sufficient enough. So they wanted this additional mass. And Daniel Libeskind is the architect who designed this new part, and they are connected. Uh, what are the main functions of the roof system? So roof is an element which is which can be composed of different components, pieces, and materials in a systematic way. So this system, it has certain functions. The first one, the important one, is to protect indoor spaces and the building products, not only the user in the indoor spaces, but all the other building products from the outer conditions, which we can summarize with this word insulation. It's the first main function of the upper part of the building envelope. And of course, uh, equally important, the other function to complete the building envelope aesthetically. Uh, and I'm sure you know this building. This is Sydney Opera House, designed by John Utzon. Here we can see this definite seashell-like structure or envelope or form, let's say, and that's obviously the upper part, which consists the roof of this building. In order to fulfill these requirements, these two main functions, the roof system must be structurally stable because it will be under a lot of loads. Uh, Here is an example. It's like a floor system. The roof must be structured to span across the space, just like the floors. And it needs to carry the related static and dynamic loads. So I'm going to provide you the first video of the Building Science 1 course. So please rewatch that video. It's both the summary of our first course last week and the beginning part of the Building Science 1. And these are the key concepts that you need to remember in order to be successful here in this course. Uh, the roof, just like the floors, it doesn't matter. The shape doesn't matter. It will span across the space uh, that will create the indoor area. And there will be loads, both static loads, uh, the weights of the roofing products, and there can be dynamic loads. All these loads will be imposed on the roof system. So the roof system must be structurally stable. In the following weeks, we are going to learn how we can design the structure so that and how we can connect or integrate the roof structure as its components, one of its components, to the building structure so that all these loads will be met and carried and transferred to the building structure safely. Let's remember the loads. As you remember the definition, I'm sure you remember the definition. Loads are all the forces that act on a system, on an object, on an entity, or a system of entities, and it may affect its either its motion or form. Before the loads are applied on the system or this object can be standing still, and after we apply it, it will start to move, or vice versa. We can stop a moving object with the application of the loads, or we can uh, change its form, geometrical form, which can be defined as deforming. And uh, here we see the example. The face starts to move and it is deformed after the application of the loads. And we have different types. First, we have static or dead loads. They are mainly the weights of building products, and it starts from the top. And each layer of the building products will uh, increase these dead loads, and they are all transferred vertically down to the earth or ground via the structural system, such as the weight of this tile. Because of the gravity, there is this constant load of the weight, and uh, they are defined as static because the level of the weight, it doesn't change, and the presence of the load, it doesn't change. It's constant. It's always there, and it's always at the same weight, and they are mostly vertical. And we can have dynamic loads, live loads. Uh, Sometimes there, sometimes not. And the level may change. If we add more things, it becomes heavier. If we decrease the number of the things, then the level of the load will decrease like that. Such as the loads of the user, or the loads of the furniture, or loads of the animals, like birds that fly or stand on the roof. These can be, again, vertical, but there can be horizontal or lateral loads, such as wind uh, and earthquake, which forces the building and this roof to move laterally, horizontally, or it can deform the shape of the roof horizontally with this horizontal direction. These are the main loads, and in order to provide the form, we don't want to lose the form, because if it is deformed, it won't function as required. Mm, We need structural system. But as you remember, there are two different levels of structural system. The first one is the element building structure. This main carcass of the building that carries all the loads and transfers them safely to the ground. But we can talk about structure in component levels, such as stairs, structure of the stairs. Stairs is the element, and structure of the stairs is one of its components. Same here, we have this definite shape of a roof, and there are some building products, heavy building products. How do they stay still like that without falling down or collapsing down? It's because of the structure of the roof. Uh, Here, when we peel off all the layers, that's what we see. The, the roof structure integrated with the building structure, so that both the shapes of the roof and the building envelope will stay still. Uh, but if the loads are applied and if they cannot be transferred or met and transferred safely, then this can happen. That's the video recording of an earthquake here. You can see that the building is stable, it doesn't collapse down, but some parts of the roof some vertical parts of the roof, they fall down, and this can be still dangerous for the uh, passerbys, and it's deformed now. It doesn't function. It won't function as required. Uh, One of the lateral loads. Uh, So different from the other parts of the building envelope, the vertical parts, the roof of a building can be directly exposed to outdoor conditions. Uh, because mainly all of these outdoor conditions will affect the building starting from the upper parts and uh, they go down, such as the sun and the rains. So let's take a look at each of them. These conditions, which must be insulated by the roof system, can be different types, and the first one can be precipitation in the form of rain or snow or hail and moisture. If our design of the roof system cannot insulate precipitation, then there will be both structural problems because all these water, rainwater and or snow will impose a certain level of loads, and the water in its liquid form or frozen form or gas form can harm building products and can cause problems in the indoor environment. Here we see an example because of the heavy snowfall. The loads of the snow will cause deformation, a serious deformation for this part of the roof, and it collapsed down. Here is another example. You can imagine how big of force it creates this mass of snow, that thickness of the snow. It can cause that like that. Uh, Another one, these conditions which must be insulated by the roof system can be wind. Again, it can create a lateral force, it can deform the roof, and it can cause building products to be deformed or broken down, and it can harm the indoor environment. Sun rays and heat. uh, as the sun rays hit the surface of the roof, because they have heating effects, uh, they can cause the indoor air temperature to raise. Uh, Sometimes, if we are in a cold climate or during the cold season, that's something that we want. But during the hot season or in a hot climate, that's something that can be dangerous for the user. So depending on the user requirements, we may want this heating effect, or we may want to pretend that heating effect. Noise can affect the roof system, all this air traffic or thunderstorms or different noise sources can affect the roof system. And if it's not insulated enough, if it's not designed correctly, it can harm the indoor environment. Another one can be a fire. Uh, Fire can cause serious problems for the uh, building. And the next one can be vegetative pests. Uh, these can be in the form of plants or animals or lichens in between, and they can harm building products on indoor surfaces. The other function, the form, color, and texture of the roof, may have a major impact on the image of the building aesthetically. Here we have this example of Süleymaniye Mosque, the design of Mimar Sinan the architect. As you can see, this upper part of the building envelope, these domes, They have a very nice aesthetic completion, let's say, with the proportions of the building mass and the whole building envelope. So we covered the main definition of the building envelope, its parts and its functions. Let's take a look at the classification of roof systems based on the forms, geometrical forms. How can we classify roofs based on the geometrical forms? We can have two different options. First, we can use lines and planar surfaces created with the lines in order to create the roofs. For that, we need to remember this is a point. It has zero dimension, and if we multiply the point in a straight direction, then we have a line. It has only one dimension. If we have two or more lines, we can define a surface. And with the combination of different surfaces, we can have a form, a three-dimensional form. Point has no dimension, line can have only one dimension, theoretically. Surfaces, without its thickness, we can only talk about a two-dimension. And the form is the three-dimensional element, let's say. We can have different lines. These can be horizontal, parallel to the surface of the Earth, or they can be perpendicular. Uh, by using these different positions, we can create different planar surfaces like squares or rectangles or triangles, different shapes of the surfaces. And when we combine these different planar surfaces, we will have three-dimensional forms, a building mass. And the upper part can be defined as the uh, horizontal surface, the roof, uh, which we call flat roofs. In Turkish, it's called teras çatı. Here, in this example, we have different levels of, we have many flat roofs at different levels of these building masses. And next to them, you see some sort of small, short walls as the borders of these flat roofs, which we call parapet walls. Uh, this is an example from Mardin. You see different levels of flat roofs up through the sloping surface. And it doesn't necessarily have to be created with lines. We can use curves, different curves, and we can create curved surfaces or again planar surfaces with curves. This elliptical surface is the roof of a kindergarten, and it has this function for the kindergarten students to play and run and learn. There are different spatial parts, let's say. Uh, I'm going to share a video, a TED Talk, short TED Talk with you. If you want, you can watch that. The lines can be not perpendicular, not parallel to the surface of the Earth, but they can be inclined with different acute angles. We can create roofs or planar surfaces, again, with these inclined lines, just like that. And if there's only one inclined surface, then it's called a shed roof, sundurma çatı in Turkish. We can have only one inclined surface that completes the building envelope like that. Or we can multiply the number of these inclined surfaces. And if they are positioned like this, one is one has this sloping surface in this direction and one has in the opposite direction, then this is called a gable roof, beşik çatı in Turkish. Uh, Gable is this triangular part that has been created because of the positions of these sloping surfaces. And this edge is called a rake. It's the name of this edge, this inclined edge. And this, sorry, there is this problem here. This line here at the lowest level where the roof ends. It's called an eave. In Turkish, we call it saçak. And this line here at the topmost level of the roof, that's called a ridge. Uh, in Turkish, we call it mahya. So these are the main terminology that we need to remember when we are talking about gable roofs. But what happens instead of using this vertical triangular surface and here and here, we can have inclined surfaces, sloped surfaces in these parts as well. Instead of two sloped surfaces, we can have four sloped surfaces and no vertical triangular parts, wall parts. Then we will have hip roofs, kırma çatı. This is a very nice example from Istanbul. It's right on Bosphorus. It's Sadullah Paşa yalısı, and the roof is kırma çatı, hip roof. Uh, as you can see, we still have ridge, mahya, we have eave, but we don't have gables anymore, those triangular wall surfaces. Instead of those, we have two more inclined surfaces, and eaves, all the eaves are at the same level here. And these inclined surfaces, they climb up till they reach the ridge point. And we have two more or four more inclined lines as the intersection of these two inclined surfaces, these parts, which we call hip or eğik mahya in Turkish. That's why we call it hip roofs, because it has hips. Or instead of in the intersection, instead of outward intersection, we can have an inward intersection, which we call a valley. In Turkish, it's called eğik dere. Either we can have hips or valleys as the intersection of different sloped surfaces. But please remember, the levels of eaves, they are always at the same level. And based on the design of the building mass, we can have ridges at different levels. In this example, we only have one ridge, the topmost layer level of the roof. But in this example, we have a ridge at this level, a lower level, and a higher level. Different levels of ridges can be created. Here we have gambrel roofs. In Turkish, we call them mansard çatı. As you can see, we have sloping surfaces, but the slope will change. Here, we have two different slopes. The first one is more inclined. The other one has a similar slope. The inclination angle is changed. We can either have something like gable roofs with these parts, or we can have the mixture of a hip roof and a gable roof. This is mainly done to create a living area here right under the roof. And with this higher sloped inclination angle, we can have a livable room with these windows just right under the door roof. Or we can multiply these inclined surfaces and create a sawtooth roof, which we call shed çatı in Turkish, because this section of this type of roof will resemble the side view of a sawtooth. And it's mainly it's mainly used in long buildings, just like factories. You know that a factory building, it needs a very large indoor area because of all these large machinery and conveyor belts and everything. This width can be stable, can have a certain width, but you can enlarge the building in this direction. You can have a longer building, but this means that the middle part of the indoor space will not get enough sunlight. natural lighting. So in order to provide natural light, you can have many inclined surfaces, and with these vertical areas, you can place windows so that you can have natural light for the indoor area, for that long indoor area. Otherwise, it will be dark and you need to use uh, artificial lighting, which will cause economical problems for you. Here, we see that we can have a very nice natural lighting with the shape of this sawtooth roof. Uh, if we connect the point or the top points of the triangles, sloping triangles, at a certain point, then obviously we will create a pyramid. That's why we call it a pyramid roof. And we can have different shapes, just like these different sloped surfaces, which we call folded plates or katlanmış plak in Turkish. And as you can see, in these types of design, we cannot separate the different parts of the building envelope as roof or walls. It's just one shell that creates the whole envelope. Lines and planar surfaces, these were the main geometrical forms. But we can use curves and curved surfaces as well. We are not just limited with the lines, straight lines, and planar surfaces. In order to create the curve, uh, again, we need the point without any dimension. But instead of multiplying this point on a straight direction, you can have a changing direction. So this multiplication of these many points will create a curve. And there are some definite geometrical shapes, such as open curves, like this half circle, circular arc, or elliptical arc, half or quarter of an ellipse. We can have, again, open curves, hyperbola, which we call hyperbola. Uh, Again, we are talking about a series of points, many points. A hyperbola is the set of points where uh, for any C and D points, any of these points, let's call this one D. It can be here or here or here, it doesn't matter. And let's call this example C, point C. And again, it can be here, located here or here or here, it doesn't matter. Any C and D points, we have this mathematical equality. The distance between point A, that's the center of these points, and point C, this distance. And if we make this abstraction, the the distance between C and B, it will be equal of the result of this other part, dA, this distance, minus dB. As you can see, there are only one A and one B points, the central points, but there can be many different D points and many different C points. And this is the set of points where for any D or C points, this equation can be equal. Both the results of mathematical calculations are equal. And that's what we call a hyperbola. And we can have one other example is an open curve that's called a parabola. Here we have again some points, the central O point, and there can be points, a set of points, which let's call this one X, but it doesn't need to be located here. It can be located here or here or here, any of these X points. If you do this mathematical equation, the distance between x and O will be equal to this axis, uh, which is parallel to this part here, uh, and xd is equal to xo. All of these x points will give the same amount of distance. So this is called a parabola. These are the open curves, or we can have closed curves, uh, circle, ellipse, and we use lines to create planar surfaces, such as these uh, horizontal or inclined planar surfaces. Just like that, we can create planar surfaces with curves as well. If we have this area filled, then we are talking about a defined planar surface, but instead of lines, straight lines, it's created with a closed curve. Uh, this is a circle, or it can be undefined, which we call an amorphous surface, amorph in Turkish, or with lines and curves. The combination of a straight line and the curve, either an open curve, half circle, or undefined amorphous surfaces. Or instead of planar surfaces, by using curves, we can have curved surfaces like this. They can be defined or amorphous. Uh, let's take a look at these alternatives. We can have a single curvature. As you can see here, this curvature has only one inside surface and one outside surface, and it's directed upwards. So there is only one curve created, this curvature. Uh, so that's why we call it's a single curvature. There's only one curve that creates the single curvature. Or we can have two or more curves, either directing towards the same side, like that, or directing towards opposite sides. But since we have two curves, we call these double curvature, same direction or different direction, or we can create an amorphous curvature surface. Single curvature surfaces can be created by using either a closed curve or an open curve and a straight line. As you can see in this example, this line is positioned perpendicularly to this horizontal surface so that uh, the curve, closed curve, circle, and if I take this line and multiply it alongside this circle, or if I do the opposite, this time I will have the line, it doesn't move, but I multiply the curve, the closed circle alongside the line, then I will create this single curvature, which is called a cylinder. The shape of the curve is cylinder. We can have different building masses or roofs using this single curvature. That's the heliotrope building designed and constructed in Germany by Rudolf Disch. And this building rotates uh, throughout the day, following the position of the sun. So if you have time, uh, make a research and try to learn about the properties of that building. Uh, we can have different examples for single curvatures. Instead of a closed circle, closed curve, we can use this parabola. Either I have a static parabola and a straight line that is perpendicular to its axis, and I multiply the line alongside the edge of the parabola, or I do the opposite. This time the line is straight, it doesn't move. But I multiply the parabola alongside the line, and I create this single curvature surface, which we call a parabolic surface. But instead of a parabola, if we use an ellipse, a part of the ellipse, then we will have an elliptic surface, either by multiplying the line or multiplying the ellipse, such as this example. Uh, I'm sure you remember this name, Oscar Niemeyer. We saw many examples of his designs. He's one of the modernist architects of Brazil. And this is one of his creations. It's a church building, and it's been designed and created in 1943. Uh, what happens if we have a closed curve, the circle, uh, an inclined line, and we multiply the line, but this point it doesn't move, uh, it's fixed, and the other point of the line follows the curve, then we will have a conic surface. These are still two-dimensional surfaces because the inside is empty. It's just an empty shell. It's not a cone. If it's a three-dimensional solid form, then we call it a cone. However, because it's an empty two-dimensional curved surface, that's why we call it a conic surface, just like the cylinder and cylindrical surface in the first example. Uh, Again, I'm sure you remember this example, Oscar Niemeyer's Contemporary Art Museum. We did this during the ramps in the last semester's course. What about the building mass? It's an upside down cone. We can use, instead of one straight line and one curve, we can use two curves, and we can create this curvature surface by rotating, not multiplying, but rotating uh, one of the curves along its axis. And if we do that, we will create a sphere. But since, again, we are talking about surfaces, so the inside is empty, it's just a shell. Uh, if it's a full uh, form, then we call it's a sphere. But if it's an empty shell, it needs to be named as spherical surface. Like that, domes, let's say. Uh, and instead of a circle, we can use an ellipse. Then we will have an elliptical sphere, just like this stadium. Uh, and we can have two curves at the same direction. We can create a curvature surface by using two different curves, double curvature. They are both looking at the same direction. So the first one is indicated with this light red, and the other one is indicated with this darker red. And when we do this, we will have a paraboloid. But since we create this shape out of ellipse, that's elliptical paraboloid. So we have two ellipses, or one circle and an ellipse, a half ellipse, and we multiply the half ellipse by following the edge of the half circle. That's how we create the elliptical paraboloid. Uh, and this example of Santiago Calatrava, he's one of the famous architects, and also he's a civil engineer. And this building has this uh, elliptical parabola. Uh, but what happens if the two curves, they are not directed towards the same side, but one of them is directed towards the opposite side, just like this parabolas. We have two parabolas, uh, and one of them is directed upwards like that, and it's fixed, it doesn't move. The other one is multiplied, alongside the first one, but its direction is the opposite, towards the opposite way. It looks downwards. So we have this thing uh, here. It's called uh, hyperbolic paraboloid. And we have an example. In this example, there is not only one hyperbolic paraboloid, but six of them, the intersection of six of them. And it's the design of Felix Candela, and it's a restaurant building. And it's created out of very thin concrete shell. The thickness is almost like 5 centimeters or something. Um, or we can have different elements, just like two straight lines and one either closed or open curve surface. In this example, we have a half circle. The circle is fixed. This first line is fixed, and the other line, which is in the other direction, will follow both the line and the circle. So this part and this part, there's a difference. Uh, this shape is called a conoid. And we can have an example uh, by the architect, famous architect, Spanish architect Antonio Gaudi. I'm sure you are familiar with his Sagrada Familia church, and this is the school building. And if you take a look at its roof, you will uh, realize that there is a series of conoids that shape the roof. So we covered the curves and curved, curved surfaces. Uh, and now let's take a look at the hip roofs and how we can express it, how we can draw it. Let's do a drawing exercise. Here, that's the hip roof in its three-dimensional view. We have eaves at the same level, and we have hips. Since the building mass is a square or cube, the base of the roof is a square. There is no ridge. All the hips, they are connected. They meet at a single point. There is no ridge line, but a ridge point. If you want to draw the top view of this roof, just imagine yourself, you are in midair, floating in midair and looking down. You need to draw what you see. So first of all, we see these edges, eaves, that create a square. And then there are hips that start from these corners and go towards the center of the square, the ridge point. And since these are 90-degree perpendicular angles, then when we create these hips, these lines, we can make sure that each of these angles are 45 degrees. So we are finding the middle point of this angle. 90-degree, the middle point, it will create 245 degrees. This is how we can think or approach to the exercise. And we know that these are all inclined surfaces, inclined towards the upper part. The highest level is the ridge point, and all these surfaces, they are sloping down towards the eave point, so we can put these little arrows to indicate the sloped direction, and we can hatch the surface so that the viewer can have a more realistic image. All the, let's imagine that this is the north direction. All the surfaces that faces north and east, that's the east direction, can be hatched with lines that are closer to each other. All the lines, all the surfaces that faces the opposite directions, west and south, will be hatched with wider gap lines so that the viewer will have a more three-dimensional visualization. And let's imagine what happens if I'm standing here. This is me, and I'm looking towards the roof. That's me standing here, my top view, and I'm looking like that. What will I see? Let's try to draw the elevation of this roof. This will be the top view or plan, let's say. And this is what we will be looking at. There is this eave, and it has a thickness. So we can transfer these lines here and transfer the ridge point here. And we need to draw the hips like that. But in order to do that, we need to remember how we do the sloping surfaces. I'm sure you remember it from last semester's course. We did that in several times during stairs and ramps. Uh, in order to do that, we need to know the slope. Let's say that slope is 20%. That means that first I need to, when I draw this eave, let's imagine that's my first point. That's point one, this point. First, I need to draw a vertical line for 100 millimeters, let's say, or centimeters, and it's here. And this is 100 millimeters, a horizontal line for 100 millimeters or 100 centimeters, 100 meters. It doesn't matter. The unit doesn't matter. And I find my second point. And at that point, I need to draw a perpendicular line for 20 uh, millimeters, centimeters, or meters, the same unit uh, for 20. And I find my third line. In order to draw the hip correctly, I need to connect the first line and the last line, the first one and the third one. And this inclination will give me 20% inclination. I can do the opposite for this part. There we go. That's the elevation of this part. And we can do the same elevation for the other directions as well. We can do the hatch. Let's try this example. Here, the base is not a square, it's a rectangle. So again, we have eaves at the same level, and we have hips. They are connected at this point and at this point, and in between we have the ridge as a line, not as a point this time, but as a line. That's the highest point of the highest level of the roof. Uh, First, we start by drawing the eaves, and then as the second step, we need to find the middle points of these angles. These are all 90-degree angles, so the middle points will give us the 45-degree. So we need to draw these inclined lines for 45-degree angles, and they meet. As they meet, they can go in a straight direction, like this one here, which will represent the ridge point. Again, we can have the narrower hatch for the north and the east looking sides, and wider gaps for south and west looking sides. We can place our little arrows to indicate the direction of the slope towards the eave. It needs to point the lower side towards the eave. And uh, if we want to draw the elevation, we need to imagine ourselves. We are standing here and looking towards this part of the eave. That's the surface, slope surface that we see. I need to imagine myself that I'm standing here, that's my head, and I'm looking towards this part. This is what I see. I can transfer that line and that point and that point and that point. First, I need to draw the eave at the same level. It has a thickness. And then I need to do the slope. Let's imagine the slope is 30 percent this time. This is how we do that. The first point, I need to draw 100 units, find the second point, and go upwards for 30 units this time, 30 millimeters, let's say, and find the third point and connect the first and the third points. There we go. That's the inclination. However, it needs to stop here because that's how long it is. And then it goes as a straight line for the hip ridge, sorry. And then we have other hip. So that's how we can draw the elevation of the roof by transferring it and finding the slope like that. What about the elevation of this side? Again, I need to imagine myself this time. I'm standing here. That's me. And I'm looking towards this side. This is what I see, that portion. First, I need to transfer these points in order to draw the eave, and then I transfer this point, and I need to do the same thing one more time. Draw 100 units for a straight line and go up for 30 units, and then, sorry, and then connect the first and the last line. But it needs to stop here because that's the reach point. So this is the elevation of our roof. Let's make one more example, a little bit complicated one this time. As you can see, we have an L-shaped building. We can start by drawing the eaves, but this time we have hips and a ridge at the lower level, a ridge point at a higher level, and as you can see, we will have a valley, inward looking connection or intersection, let's say. We start by drawing the eaves. You can do this exercise with me if you like. You can get a normal square paper and draw this. Uh, these are the number of the squares that you need to count. So this side has 6 squares, this side has 6 squares, 3 squares, 3 squares, and 9 squares with these perpendicular angles. So we start with finding the middle point of the line, the angles. This is a 90-degree angle. So the middle point will give us 45 degree. Again, this is a 90-degree angle. So the middle point will give us 45 degree, 45 degree, 45 degree, 45 degree. Okay, how can I go here? What should I do here? Should I go this way or that way or other way? The rule is find the middle point of the angle. Here, we don't have a 90-degree angle. It's more than 90 degree. It's 135 degree. Sorry, 275 degrees, something like that. We need to find the middle point of this angle, and that's how we need to go, like that. Okay, so that's it. I just create longer lines and I see that they are connected at just one point, ridge point, and we can call these like 45-degree lines because they are inclined like that. There's this rule, if two 45-degree lines meet, they need to go towards the 45-degree angle. They cannot go straight, but they need to go towards either side of the 45-degree angle. So we already have this side. It needs to go this side, like that. As you can see, these meet. So we have two 45-degree angles like that. Two 45-degree angles meet. They need to go straight like this. And if a 45-degree and a straight line meets, it needs to go 45-degree. That follows the direction of the 45-degree. So we have these rules. If two 45-degree meets, it needs to go straight. Rule number one. If one 45-degree and the straight line meets, it needs to go 45-degree, it cannot go straight like this. It needs to go 45-degree, but which direction? This one or this one? We need to prefer this direction because we have a 45-degree angle, not this direction. The second rule, if a straight line and the 45-degree meets, it needs to continue with 45-degree towards the 45-degree. That's the second rule. By following these rules, we can draw the top view of a hip roof. It doesn't matter how complicated it is. And once we create the top view, we can draw the elevations easily. So let's take a look here. The same thing. So it's completed. We need to do the hatch and the arrows towards the eaves. And now I need to imagine myself. I'm standing here and looking towards this roof. There are two inclined surfaces. The first one is closer to me, so I can start with that one, this one here. In order to draw that, I need to transfer the eave and draw the eave first. And then I need to do the slope. Let's say this has 45-degree, not degree, sorry, 45% slope. Then this is what I need to do. That's my first point. I need to draw 100 units, find the second point, and go upwards for 45 units this time. Find the third point and connect the first and the third one, and transfer the ridge point. That's my this hip, and then it goes like that, and we have the eave. So it's completed. And then there is this other surface. I still see it, but it's a little bit further away from me. So we can do the same. First, we transfer it. We know that all the eaves, they are at the same level. So this is the eave. The slope is the same, so we can draw a parallel line to the first one, like that. And we can transfer that point. So that's where the hip point is. And from that point, it needs to go that way because we have this other hip. And they meet here. Now you can see it in a better way. That's the first part, this red part, and that's the other part. As you can see, I just leave a small gap, and there's a little line weight difference in order to indicate that the viewer can understand this surface is closer to us, this is slightly further away, and we can have the hatch with the same gap, and we can draw this elevation. Again, we need to imagine ourselves that we are standing here, and this is our head, and looking towards this direction, and we are here and looking towards this direction. So a closer surface, a further away surface, this one here. First, we do that by transferring the necessary things, and then we leave the gap and change the line width slightly so that people can understand. Uh, Here in this elevation, there is only one surface, and in that elevation, again, there is only one surface. So these are the basic exercises. Please do that. And if there's a problem, we can talk about during our next lecture. You can ask me questions. So that's the end of this video. Hopefully, next week we are going to examine the answers for these questions. What are the basic components of a roof, and how can we manage all these components, all these different products, layers, to stay where we need them to be? We need a structural system for the roof as one of its components, and we are going to learn how we can design, create the structural system of the roof. Okay, thanks for listening. Hope to see you next week.